We warmly welcome you to this special day where history books of our university will be written in golden letters. It is the day we initiated the ACM student chapter of our university. And it is the day where great Professor Abhik Roychaudhury came into our university and delivered a great speech. I know everybody is eagerly waiting to hear his speech. But before that, we have some small things to be done. We will start the session by lighting the traditional oil lamp. For that, I would like to invite our distinguished speaker, Professor Abhik Roychaudhury, Lieutenant Colonel Dr. Chandran, Head of Department, Computer Science and Engineering, Mr. Johan Kalikala from Koche, Mr. Lila Priyashandra from MIT, Chair of ACM Student Chapter, Himesh Silva, Batch Representative from 10th Batch, Hasini Sinara, Batch Representative from 11th Batch, Madhavi Nigam.
Good morning, everybody. So I'd like to welcome Professor Abhik to the University of Moratuwa again. So he's actually not the first time visitor our university. He's the Vice Dean of Research at the MIS School of Computing, and we have a MOU with the school for continuing development in academic and research collaboration. So I'm very thankful to Professor Abhik for initiating such very useful and productive interaction with our department and the university. And I would like to thank the student chapter of ACM and its committee for taking the necessary steps to organize this talk, because this is the kind of things that global universities does. And in NUS we have a top class, world class university. So professors in that university go around giving talks around the world. So one day hopefully professors here go and do the same thing. But meanwhile we are very fortunate to have Professor Abhik coming and giving us a talk in an area of extreme importance to us in software. And so this is part of the activities that the ACM student chapter of the University of Moratuwa is organizing, and we are hoping to have many more such activities in the future. So once again, I would like to thank Professor Abhik for accepting our invitation and coming to Sri Lanka and to University of Moratuwa. Thank you.
Thank you very much, sir. Now is the most awaited moment. But before we move on to the main segment of our event, let me introduce you our distinguished speaker. But mind you, it will take some time. Professor Abhik Roychaudhury is an associate professor of computer science and vice dean graduate studies at School of Computing, National University of Singapore. He has been at the National University of Singapore first as an assistant professor and subsequently as an associate professor. He has published more than 100 papers in premier conferences and journals. He has authored a book called Embedded Systems and Software Validation. It has been adopted for teaching at different universities all over the world. His research has been recognized by various awards and honors, including ACM Distinguished Speaker since 2013. ACM 6 of this stream is paper award and IBM faculty award 2008. His research has been funded by various agencies and companies, including the Ministry of Education, A-STAR, Defense Research and Technology Office, DSO National Laboratories, Microsoft and IBM. He has served in the program committees and organizing committees of at least 50 conferences, including Real-Time Systems Symposium International Conference on Software Engineering and ACM 6 of Foundations of Software Engineering. And he is currently serving as an editorial board member of IEEE Transactions on Software Engineering. And there are a lot of things to say about this great personality. I don't think time permits me for that. Ladies and gentlemen, it is the big moment. Please welcome, with a big round of applause, Professor Abhik Roychaudhury on stage.
Thank you very much for taking the time to listen to this talk. It is indeed my great honor to visit this university, where I have visited also in the past. And also this university, in particular, we have interacted with the Department of Computer Science. This university is one of our valued partners in research and graduate education at the National University of Singapore. So for me, this is, apart from giving this talk, it is also a very good opportunity to visit the university again and reconnect with the professors and past students whom I have met in past trips or during their visit to AWS. So this is indeed great. I will talk about this topic. Actually, the way it works in the ACM Distinguished Speaker Program, we give out a number of talks, and when it is requested, one of the talks are requested. So I'll talk about that one. Specifically, the title of the talk is Software Debugging as a Science. So let me just give you a bit of an outline. Sorry, this pointer. So before I go on, I guess this is the mandatory material. I think this is important for me to present about ACM. ACM, as you know, the Association for Computing Machinery. This is the world's largest educational and scientific computing society. So, Society in Computing, this is the world's largest educational and scientific computing society. And it supports the professional growth of its members through different ways, lifelong learning, career development, professional networking. For example, this month, the speakers program is more of a professional networking opportunity, both for the speaker as well as the place where the speaker is visiting. The Distinguished Speaker Program, it is actually made possible by the Association for Computing Machinery. You can, if you are interested in this program, you can visit this website, okay, and find out more about it. Yeah. Okay, so I start my talk now. My core area of research always, even though I have applied it in different dimensions, has always been in software testing and analysis. Okay, so this is really where I belong, software testing and analysis. And now once you start working in software testing and analysis, you have to apply it in different ways. And one of the domains where I have applied it is embedded software, because many testing and analysis problems kind of come out in nice ways there. There are other research that comes along. For example, when you make some small changes in the software, if the software was working earlier, it does not work anymore. That is called a regression. So understanding the root cause of these regressions is fairly important. This is something I have worked with. Nowadays, in the software testing or software engineering research community, there is a lot of interest towards at least fixing the bugs automatically for the very simple ones. This is again something we are looking at the National University of Singapore and also in other universities. So these are some of the dimensions of software testing research that, if I may say so. And in future generations, one can envision programming environments where at least the simple errors the programmers don't issue of debugging as an activity and its importance, I think this is easier to see. Some of the study methods that have been studied, but maybe it is still not being deployed as much in the industry as it should be. And of course, the specific problem that I would like to highlight, the issue of debugging software regressions, because this is something which is very, very everyday. Every day, it's not that unless you are working as a student and in the first year and trying to develop a programming assignment, which is very, very simple. Apart from that situation, if you are working in a company, you already have a code base and you are just trying to make some changes in the code base rather than trying to write things from scratch. So when you try to make changes in the code base, something fails and you would like to know why it failed. Okay, so let me start with something, a little bit of the technical material, not too technical. So this is one of the software design flows in which you might have followed, possibly say in a software engineering course in your university, since many of you are students here. So where there is the user and the requirements are written in natural language, and then there are some desirable properties, and from the requirements, this is really almost manual step where you will generate a design model, and then the design model will be used as a guidance for the purpose of code generation. Okay, so this is possibly something you might be familiar with. And then of course from the code you try to do testing, and then subsequently when the test cases fail, you debug. This is another design flow, which is quite different. There is no design model here, and oftentimes this is the case. Even though in the university we are always told to construct our design models in UML and so on and so forth, when you actually go out, you don't always write down these design models. Okay? So this is another design flow, and we realize that there is a programmer, and the programmer might be directly writing down some code, but there would also be some desired properties, and sometimes you can get these desired properties by mapping the test cases. And how you can actually debug the code, this is another issue. So in this case, when the programmer directly writes down the code, there is also this additional possibility, I won't be talking about that today, but there is also this additional possibility of generating some abstract code. From the code you perform some abstractions to generate a model, and then you can verify properties about the model and say something about the code. So this is a very exciting domain. I will not talk about that today, but there has been work in this direction, at least for special classes of software like device drivers, and Microsoft Research, for example, has worked quite a bit. Okay, so at the onset, before I get into debugging, it's very important to clarify this terminology. So I feel that many times when we talk about debugging, these two scenarios on the left-hand side of the slide and the right-hand side, these are really very stuck. So in this case, if you look at the left-hand side, you just have an input and you observe the output, and the output is unexpected. And then you try to say that, oh, I had expected, you scratch your head and say, I had expected that the output should be greater than the input. And then you try to find out why it is not for this particular test case. So this is really the debugging problem. When we are doing software development, this is really the debugging problem. Okay? Whereas this is sometimes also referred to in some, at least some research papers, as debugging. Whereas this is really bug hunting, where you have a program and you have some desired properties of the program. So this is written in a formal language. But what this is saying is, when the program reaches the end, the output should be greater than the input. Okay? So you have some desired properties of the program and you feed it into a checker, like a model checker. And this gives you a counter example. So this one says that, well, for these values of input and output, the property you had in mind is not satisfied. Okay? So this is really bug hunting, and not really, this is not what I'm referring to as debugging. And if you think about it, conceptually these two activities are very different, because here you have a very good idea about what the program should satisfy, what property the program should satisfy, whereas you do not have a good idea in this case. Okay? Here you are generating the trace, whereas here you start with the trace. So these two activities really have a Okay, so of course there are many issues, there are many terminologies. If you just go to Wikipedia, you will see that there are many terminologies on what a bug is, and debugging is referred to as finding a needle in the haystack. Okay, so but hopefully you can do a little bit better than that. And I'll try to quickly go through some of the deficiencies in the debugging literature in the past. So this is actually a quote from more than 10 years back, from Brent and Santana in the IBM Systems Journal. So we have mentioned that debugging remains very much an art. Much of the computer science community has largely ignored the problem. Over 50% of the problems resulted from the time and space chasm between the symptom and root cause, or inadequate debugging tool. So this is often seen as a very ad hoc, very industrial activity where any research does not need to be done. It can just somehow be solved as an ad hoc mechanism. So really speaking, what is missing in the current state of the art or the state of the practice that is available? We can look into that. So I believe what is missing is this, that currently the tools that you are using are of this form, of this metal detector, where you can say that, oh, there is a needle in the haystack, but it really doesn't point you to exactly where the needle is, and this is really the problem. Okay? So I'll try to motivate the need for these important tools and try to hopefully give you some idea about what kind of tools we can develop. So this is one kind of tool which all of you might be familiar with. All of you have worked with some form of GDB. Okay, this is the JDB, more of the textual interface. This is another kind of tool. This is again the GDB in Linux, where you have this. You set these breakpoints, and the programmer explicitly sets the breakpoints and observes the program state. This is another one, in this case in MS Windows XP with Visual Studio, and you can actually have more and more visualization of the program state. Okay, so what is really missing? So oftentimes people tend to think that as if there is some more visualization is put into it, if there was a better GUI, then the debugging problem would be solved. Of course it would not be solved. Okay? So it's not the issue that there is any lack of any GUI or there is lack of any visualization. You can keep on collecting information and you can keep on visualizing information. And to some extent that does happen, but that's really not the issue. And there are these command line tools for Java or any other popular programming language where the user can set these breakpoints, replay an execution, watch at the breakpoints. This is certainly possible. But really speaking, what is missing is the lack of automated analysis, and this is currently left to the user to do. And much of these activities can be automated. So I'll go through this. I don't think I need to motivate this too much, the importance of debugging. I'll go through this relatively quickly, just to give you an idea of some studies that have been conducted. I think this I don't need to motivate, and there is a social aspect to it, because And if you assume a linear scaling up of errors, usually it does not scale up linearly. The bigger the project becomes, more errors will create. Okay? And if you assume just 1 hour to fix each major error, okay, usually it's much more than 1 hour. 1 hour is not enough, as anybody who has done debugging. This is actually this salary number I got from the Infocom Development Authority website in Singapore. Okay, but the salaries can be different in different cases. Yeah, I can see that some people suddenly became interested just when I mentioned the salary information. But when I was mentioning about debugging, right? So given the salary and this kind of a linear scaling up, so I have all of these calculations I have done very, very conservatively. You can see that this costs the company just for this kind of errors at least this much. Okay, this is actually very conservative. It would be much, much more than that, simply because this 1 hour is not a proper estimate. It takes much more than 1 hour to fix a bug. So I'll move into the methods now. What can we do to improve the situation? How we can get out of this breakpoint-based debugging of GDB and move into probably better tools that can be integrated into future generation programming environments. Okay. This is a fairly old method by now. I worked on it more than 10 years ago. This is a fairly old method by now. I worked on it almost 15 years ago. And then there are other kinds of methods like trace analysis, which are also now slowly getting older. And these are some of the relatively newer methods which have been found to be scalable. So I will share some of these methods and try to hopefully try to have some discussions with you on how feasible it is to integrate these in the future generation programming environments. So this is the old method that I promised. It's actually extremely simple. You have an input, you feed it to a program, it generates an execution trace, and then there is this method called slicing, which goes through the execution trace and gets program dependency information. I will try to clarify in a minute what's the program dependency information, to give you some of the statements in the trace which were related or relevant for producing the raw output. Okay. So how does it work? We can look at a simple example. So of course the method takes a trigger first of all and input. Okay. In this case I have already shown you the execution trace of the input for this particular procedure or method. Okay. And it also takes in a slicing criteria. The slicing criteria, you can think of it as asking of some why or why not questions between the programmer and the tool. So the programmer can ask the tool, I expected x greater than 0 here, why is it not? So you can ask this kind of why or why not questions using methods like this one, and the tool will try to answer that in an iterative fashion. Currently, if you think about it in the breakpoint-based debugging, this is completely manual. The programmer is asking the question and also trying to answer the question by rerunning the software and trying to observe the program state. So here, this is the slicing criteria. So this is the question that the programmer is asking the tool, that I had expected a different value. Why is it unexpected for line 6? Why is the same value unexpected? And what the tool can do, it can say that, well, this is because you got the value from here and maybe this is wrong. Okay? So in the slicing terminology, this is called a data dependency. And this is why it is a data dependency. It's easy to see because this is really the definition which is being used here. It is this definition that is reaching here. Okay? So this is not particularly new. And then you can say that, well, why did I execute this definition? That was because this particular branch was evaluated in a certain direction. And again in the slicing. And then in this particular case, there will be one more data dependency because this branch was evaluated in a certain direction because it got the value from the parameter. Okay? So by taking the closure of all of these dependencies, it will, in this case, just leave out this particular line. And the other lines did not get that much savings. We only saved the looking at one particular line number 5. But my purpose is to show to you how this kind of a technique works. It tries to essentially answer these questions about why this value is unexpected. So you can think of this as a dialogue between the two-level programmer. Why is this unexpected? This is unexpected because it got the value from here. Why it got the value from here? It got the value from here because this branch was evaluated in this direction. And why this branch was evaluated in this direction? This was because the parameter value that was passed was responsible for it. So this dialogue is being done in one shot, sort of, and in an automated way. It can be done if the programmer instructs the tool that give me all the data and control references. Or the programmer can decide to be more selective and try to look for specific patterns of the data. But this is certainly better than working with GUI, where you have to set the breakpoints yourself, rerun it yourself, and observe the state yourself. So in fact, as I mentioned, this is something we worked on quite a long time back. And, in fact, the tool came out in 2004. We finished this in 2004 in EC, International Conference of Software Engineering in 2004, which was 10 years back. We presented this kind of an architecture. Before that, it was considered that this is more like a theoretical method, and this is not really scalable for full general purpose programming languages. We worked it out for the full Java. And this is really the structure. The reason we would scale up for a full programming language, because I really want to see these techniques impacting the practice in terms of software development rather than just in the research. And the reason we could scale it up is this particular block over here. As we execute the program on, say, this JVM, we also generate this bytecode trace, and then this goes to an online compression. So you never try to store the entire trace. And this was quite responsible for scalability. This is what gave us quite a lot of scalability. And this is the criteria, as I said, that is input to the technique. And of course, because of Java stack-based architecture, we had to do some stack simulation to actually get the dependency. So of course we tried this, as I said, this is for the full of Java. We tried this on many, this is just a this is very old. We tried this on many more, and right now it's not just a question of we tried it, many others have also tried it. We distribute the tool for free. And the slice size was found to be between 1 and 10% of the program. This is the time. And this is what actually gave us a lot of the scalability, which could be scale it up to the full scale programming language, say 30 to 3,000 times. So these were some of the technical innovations which actually enabled us to go from being a theoretical technique to something that takes it to a full programming language. I'm not going into the details of each of these innovations, but just to mention them, there was an online trace compression. You cannot generate the trace and compress it, because of already if you generate it, you will run out of memory. So you should online compress it. As it is being generated, you should compress it. And all of the analysis was directly done on the compressed trace without ever decompressing it. If you think about it, this is not trivial, because you want to make sure that when you do the analysis on the compressed trace, there is really no loss of information. Okay, it is the same effect as doing the analysis on the decompressed trace. So that was quite difficult, I would say. But I'm not getting into the technical details. The program dependency analysis was done on the compressed trace, as I said, without any decompression. And also, the analysis had to be done at the low level, at the bytecode in particular, to support third-party software. Because you might have portions of your program which is written by others. You might not be developing the whole program. Many of these analysis, the debugging techniques, they often work at the source code level. But I personally feel it's always better if your technique can work at the bytecode or the assembly code level. If it is C, then maybe the assembly code level. And we have in particular worked on many debugging analysis techniques which directly work at the assembly code or the bytecode level. Because then that is something that allows for integration of libraries or third-party software provided by others, which is a very practical issue. It's a news in many places, so let me not belabor this. This is very old data. Since then, many other users have joined the community. Apart from research from many other places, it has been used for software development, from teaching, of course, just to convince you, also outside the US, not just in the US. And this is very old. I did not look at the user list. This is 5 years old user list. So there are many other users who have joined and who actually just inform us how they are using the tool. Okay, so what does it do? Just to kind of give a quick technical roundup, it helps in the program comprehension, in automated debugging. Of course, the debugging comes with testing. There is this technical innovation, and of course, it covers the entire Java programming language. So, maybe one particular point, not a fully technical one, which I thought is useful to illustrate, particularly from the company perspective of using debugging. This point I think is very important. If you are really working in a company and using any of these testing debugging tools, that these also help in the program comprehension. Software testing, it is not just for testing the reliability of the software, that it also helps in the program comprehension. This is quite important. So I was once given quite a bit of funding by a company, which will go unnamed, for this purpose, because the problem that this company was facing is that this is a large company which often acquires other companies. Okay. Now when they acquire other companies, they have to take over the software that was written by those smaller companies. Okay. So now this big company personnel has to go and have a very stressful meeting with the small company's personnel who were managing, maintaining and writing that software. So that meeting is actually not necessarily a very pleasant one. It could be a very stressful one because the small company's person might have lost his or her job because of this acquisition. Okay. So this is a real issue involving real people. So now any of these big companies who are going through these mergers and acquisitions, they have a real problem because they are supposed to take over this software and they have no idea what to do with the software because sometimes it is not even properly documented. And they were very interested, and subsequently I would say they were successful in terms of the research, in using the research that we did. They were very interested in how testing technology can be used, testing and debugging technology can be used for software comprehension. Because you can, if you have a good test case, good test suite that you can collect, then you can just run the software for many of these tests and observe the output of the software. And from there try to reverse engineer a model of what the software is doing. And that already gives you an initial idea of what the software is doing. Okay? Even though you have access to the source code, you are now the boss, you are now the owner of that software. Even then, it's such a huge code base, you have no idea what it is doing. So, testing techniques can come to the rescue. So, you can just run test cases, observe the output, you can, if necessary, debug the test cases, and then from the output-input relationship, input-output relationship, you can reverse engineer a model which gives you an initial idea. And in particular, with that company, I worked on something a bit more reliability. I think one important usage of the techniques in the field is often in program comprehension, just to find out what a software written by others is doing. This one may be the situation I told you just now of merger and acquisition. This might be a little bit dramatic. But these days there is software outsourcing. Yeah, there is global software development. It is never written in one place. So if you are working in a team, the software components written by others sitting in another country, for that also people are now using testing. So this is where some of the testing and debugging research can be used beyond the software reliability. So I just want to share this experience with you as I move on. Okay, so apart from slicing, people have also in the research community looked at this trace analysis And if the branch condition is wrong, then you would compare this particular execution trace with another execution trace where maybe this branch is evaluated differently, and you would try to find out the differences. So this would help highlight to you. So if you think about it, even though the idea appears very deceptively simple, this is quite fascinating. Because most of the times, what is the problem in debug and testing? The problem is you don't have a formal specification of what the program is supposed to do. If you had a formal specification, then many of these activities would become quite trivial. The trouble in the field is that you don't have a formal specification of what the program is supposed to do. So you don't have an idea, a clear idea of what the correct program is supposed to do. Apart from how this test case is supposed to behave. So in this case, when you have this failing execution trace, all you are doing is, even though you do not have the correct program, you are trying to take another execution trace from the buggy program itself and hoping that it will simulate somehow the correct behavior. So this is the intuition behind some of these anomaly detection based methods, that if this run is somehow anomalous and I could find out another successful run which is different from this, which is quite close, then I could somehow compare the two runs and probably do some anomaly detection, and that would probably point me to a bug input. So I just wanted to mention these kind of techniques with you. I have also worked with these kind of techniques, but not as extensively as some other research groups, as extensively as I have worked on the slicing. But this has been pursued by other research groups. And my purpose here is really to give you a roundup of the different debugging directions rather than only the research that I have done. So usually this is how the techniques work. So given a failing execution trace, you assume that there is already a test suite that is available with the program, which is the case of industrial software development. And then you could actually either generate a successful run, or you could choose from there and you could compare the executions and give the bug report. This is how these techniques actually work. And this successful pool of runs could be either obtained from the test suite, or it could be obtained from a perturbation of the failure input. So there has been a lot of research on this, which is also now quite relevant. Okay, I'll finish up by mentioning this particular kind of testing and debugging called regression testing. I guess if you just Google on regression testing or regression, it will point to many websites. Regression testing is an important topic, and this is fairly important for any software development which happens in real life, regression analysis. Because as I mentioned, the way the software development happens in the industry is not that you will of course develop something from scratch. Usually it happens by checking in of program versions. You have to make some changes, you have to check in. Okay, there is a typical check-in or commit procedure, you have to check in, and sometimes the code that you check in, it might not even be accepted. Right? You probably know. If some of you have worked, you will know. It might not even be accepted, and you have to go through some discussions to make your changes be accepted. Okay. So I'm getting a little bit into the nitty-gritty of this, because this is something which is very important for industrial scale software development, and how the research can help in this. Okay. So when I was a very small child growing up in India, I remember there was this Sunday newspaper, okay, and they would point out two pictures which are very close and which had exactly 6 differences. And then I would always fight with my brother who would find out the 6 differences very quickly. Okay? So here there are some differences between the 2 pictures. Can you spot the differences? Yeah? Maybe our organized image can you spot the difference? Even if you found out the differences through a diff tool, you could run a diff. Even if you found out the differences, you would not know whether they are responsible for the particular failure that you are facing. Usually there are differences in thousands of points between two major versions. Yeah? So this is a real problem that any development field, and when I wrote a paper on this, this is something I mentioned in the paper also. This is a real problem which any development field in the world is facing. Okay? So this is not some concocted problem concocted by researchers. So manual code review clearly isn't enough. The cost of managing software evolution, okay, this is known by now. The cost of managing software evolution takes large percent, and it is speculated that currently in any large software project this is about 90%. So only 10% of the developer's time and resources and salary is going into the actual development, the requirements and installation, development and so on. The front end. The front loading is only 10%. And then the back loading, which is that, oh, this is failing, go back. Oh, no, not yet, go back. This is 90%. It's a huge cost. Okay? So finding the root cause of this regression bugs, this is really a major headache. This is a big issue faced by all of us. And of course, this is the regression that happens in software development. Okay. So let me just skip this one. This is just a real example. There are, I guess any of you would know that there are a lot of these real examples. So this is really the regression debugging problem where a huge amount of time is spent, a huge percentage of any software development is spent. That essentially there was a test input, previously it was passing and now it is failing, and why? Okay? And in fact this is the work that we have done. It was done a little bit earlier, but the paper in the journal came out in 2012. And this one also received this Sense of Distinguished Paper Award because of its relevance to the real world software development. So I'll talk about this approach a little bit. But before talking about this approach, let me run through some of the more obvious solutions we can think of probably. You can probably say that I will run a diff between the two tools and I will look at the subsets of the diff. Okay? That is possible. But of course there will be just too many subsets, as you might imagine. If you do the subset construction, there will be many subsets. This is really not good. If you are talking of actually your method, your research having an impact on the industrial software development, this really will not be possible. And also this requires defining the set of all changes. You might say that this will be done by program versions that will do the diff, but sometimes you can have two different implementations of the same protocol. They are implementing the same specification, like two web servers. They are implementing the HTTP protocol. Okay? But then the implementations might be completely different. They might be using different algorithms, different data structures. If you do a diff, almost the whole thing will come as a diff. The trace comparison, we already talked about trace comparison. Could this be used? Okay, you can see that it cannot be directly used, unfortunately. You can compare failing trace with a similar successful trace. But the question really is, if you try to do this at a very large scale, how do you even find such an execution? How do you find the successful execution? There are so many of them. There could be millions of successful test cases and a few hundred failing test cases. It's very difficult. If you have done these things in the field, you will realize these are really difficult problems. And of course, you don't want to ignore the evolution also. You want to take the past program version into account. So the solution we looked into, which subsequently scaled out very well. I won't be discussing about all the results, but just to give you an idea of the scale, we subsequently used this to find out the root cause of errors in the whole of the embedded Linux by comparing it with the normal Linux, the GNU core utils. So it is at that scale that we are doing these things. The solution was by adapting the trace comparison idea. So we have a test input, fed to both of these programs. We don't want to directly compare them. Instead, we want to see whether we can somehow generate a new input which considers both of the program versions. Okay? And how do we obtain the new input? So this is really the idea. We have an old program and a new program, and this is the failing test marked in red. We are trying to generate a passing test like this one, marked in black, which is similar to the failing test in the old program, but now is different in the new program. Okay? I'll give some more schematic of this. And one notion of similarity would be if the tests follow the same path, but subsequently in other works we followed other notions of similarity. My purpose is just to give you the idea, shared idea, and of course there might be many manifestations of this idea, which we have also pursued and others can also pursue in subsequent research. So this is really the schematic. This is a fairly important slide, so I request you to pay attention because this is really the key to the idea. So this is the schematic. This is, say, the partitions of the inputs, and we say that two inputs are in the same partition if they are similar. And the definition of similarity for now is if they follow the same path, you can consider other notions of similarity. So, really speaking, given this buggy input which moved from one partition to another, I am trying to somehow generate through some method an input like this blue input, which was behaving similarly to the red input earlier, but now is different. Okay? So if you watch carefully, if you pay attention, you will see that the blue input has not changed its behavior. It is in the same partition. It is the red input which has changed the behavior, and this is the bulk. Okay? It is the red input which has changed the behavior, but by comparing its behavior with the blue input, I will find out that it has changed the behavior by it was in this partition and has moved to this partition. This is how I will find it out. But my goal is to do that by generating this blue input. Okay, and then subsequently you have that intuition, the solution was quite straightforward subsequently, that essentially given these paths for the tests in the two programs, we generated this so-called path condition. The path condition is a logical formula which captures the set of all inputs which follow the same path. The set of all inputs which follow the same path. Okay? So we calculate these path conditions, and nowadays there are these satisfiable modules of the resolvers. That technology has become pretty mature. So we could compute these very efficiently, and then we have to generate the blue input. We are solving this formula that inputs which follow the same path as the buggy input in the old program, but follow a different path in the new program. Okay? And then we generate the new input, and then subsequently we can do a trace comparison. Actually, in later works, we found out something better than doing the trace comparison. But here I just want to give the general idea without getting into all the technical details. So in fact, this was the overview of the solution. Let me not go into all the details. So we compute these path conditions, which is the set of all inputs which follow the same path as the buggy input, and compute these formulas as well as the dual. There could be many solutions to the formula, and we also have a way of taking care of that. In fact, there could be infinitely many solutions, so we have a way of partitioning it into finitely many partitions. Okay, I just run through one simple example and then I conclude. So for example, consider this error. This is a code missing error. So by mistake, I missed this out. Okay? In this case, I have commented it out. So these are the partitions. So in this case, we can see these inputs, they follow the same paths. So they are in the same partition. They follow the same path, they are in the same partition. And here these are the partitions. Since once one branch was removed, the number of partitions here has reduced. So how do I find out explaining inputs or inputs? So I calculate the path condition. So in this case, this is the path condition. You can see if you feed input equal to 100, this branch will be evaluated to true, and this branch will also be evaluated to true. So all inputs will satisfy this condition, input greater than are taking the same path. Okay? And all inputs will satisfy this condition here. They are taking the same path as the Barbie input. So then I saw this formula, but this is actually unsatisfiable. And the dual formula, which gives one solution, it actually could give more solutions, but they will produce the same path. And then in this case, I could actually compare the two traces to the alignment at which exactly points to the Barbie line, which is the input greater than 9, which was missing. Okay? So these are the two parts in the Barbie program, but this input was generated by considering the previous program version. Okay? So this is an example. I just gave you one example of a code missing error, which are notoriously difficult to find out by any debugging technique. Why? Because if the code is missing, you cannot probably hope to just analyze the Barbie program and find out the code that is missing, right? I think this is common sense for all of us. If the code is missing, how can you run debugging on the Barbie program? Where it is missing, how will you find it out? Yeah? So for these kinds of analysis are quite useful, where they do the regression analysis and consider both the program versions. In fact, this is the first implementation. There are many implementations of this one at a very large scale. As I mentioned, I am a strong believer in building all of these analysis and testing techniques which work at the lowest level, at the assembly code level. Here, our debugging method is actually working at the assembly code level. Okay? We do the binary execution trace, and here we do all of this symbolic execution, path emission, extraction, dynamic slicing, and so on. I should thank this group, Place. They have subsequently made their software available, but even before they had made it available, they made it available to us, because of which it was possible for me to do this research and quickly build up the infrastructure. Because as you might imagine, for doing these things in a large scale, the analysis infrastructure I need is huge. And of course, I was running against time, and I don't plan to spend years and years building up all of the analysis infrastructure. So they provided some of these useful components, in particular the symbolic execution, because of which I could quickly build up the whole analysis infrastructure. This is quite scalable. This 10 virtual machine here, this can take in both Windows and Linux binaries. So it can treat both the Windows and the Linux as the guest operating system. These are some of the experiments just to show you, but there were many other experiments that we have done, which I am not discussing here. This is just to show you the scale. This is at a very large scale here. The Apache web server, this is in particular notoriously large. So this is about 358K. Subsequently, we did very large scale experiments, even larger scale experiments with the whole of Linux. There are published errors in embedded Linux, which people have not found out the root cause of, in very common utilities like printf, tr, etc. So things that we use. And we use this technique or different manifestations of it to find out the root causes of it, which are even larger scale. So scale is really not the issue that we faced, even though we had to work very hard to keep it scale. Just showing you one particular error in case you find it all very abstract. This is one of the real errors that we found. So I'll just go here. So in this case, actually, this else if this is the problem, it should have been if length. So since this is an else if, since the if was turned to an else if, this particular length check was missing. And since this length check was missing, this was leading to a buffer overflow error. And that could be remotely exploitable. The buffer overflow in this case could be remotely exploitable by an email client, for example. If you get so this lib page, this is a library for reading and writing PNG pages. The PNG has shown the PNG format. Right. Okay. calls the PNG get UIT 32 and does necessary checks. Okay? So if you directly just call the PNG get UIT 32, again you will be missing these necessary checks, and this was one of the errors. Okay? This might be remotely interesting. So you can see, of course, if you give a getx query to a web server in Apache, it will give you an invalid request because this is not a valid URI. It should be invalid. X is not a valid URI. Whereas this one, this mini-web, this is actually a resource constrained web server. It by mistake returns index.html. It accepts this one. Okay? And one of the things to highlight is that we were able to compose all of this, which pretty much none of the syntactic kind of debugging methods would be able to do, because these are completely different implementations. Completely different. So if you just do a diff, the whole of mini-web will probably come as a diff. I really cannot underscore the importance of semantic analysis here. Okay, so that is pretty much the end of my talk. Just to give you the highlights of some of the important concepts, all captured in one slide. If you want to take home one slide, maybe this could be the slide that you take home. Of course, there is this importance of debugging, and we need not keep it at home. This is one of the simplest debugging methods, the slicing, which encapsulates the intuition behind the GDB. The GDB we do debugging completely manually, and it automates some of the intuition. This is the trace comparison-based methods which have been looked into, and subsequently how the trace comparison-based methods have been adapted for debugging software regressions. Okay, so this is pretty much it, and I think that's what I leave it here. If you want more extra, there is also I have this book on embedded systems and software validation. You can read it if you wish. Yeah, but let me conclude in this slide. We have used the working group's infrastructure and built on top of it. So as I said, some of the components from them we are using, without which it would have taken us a lot more time. So the debugging method is due to us. The infrastructure is due to them. Because their infrastructure is not for debugging. Their infrastructure is for security vulnerability detection. But for the security vulnerability detection, they have implemented many components, many analysis components, which we could reuse. They are not working in debugging at all, or for that matter in software engineering, but their thing is vulnerability detection. But as you can see, the two areas have linkages, so we could use their components. Yeah, I would say so it's more the method that we are liking. So they have the individual components, but they have not, of course, considered putting together these components for debugging in any way. They have the individual components for doing something else. Just like you can have software components and you might be doing a different task, and somebody can come and say that I could reuse some of your software components and I will do something completely different. So they had, in terms of the components, in terms of the components, I would say that this is the component which we definitely will use, the symbolic execution. Because the symbolic execution, as I said, it was very important to do it at the assembly language level. And they had a fairly worked out symbolic execution component, which was useful because at the x86 assembly language level doing the symbolic execution, that's a lot of work. So that component we could directly reuse, and that was very useful. Otherwise we would have to implement it ourselves. That would have taken us I did not look into that. That's actually an excellent point because nowadays there is more and more need. I have not looked into that, but this last technique that I mentioned, so just like software regressions, they can happen in multi-threaded applications as well. And sometimes it could be that the specific error is getting manifested for a particular thread schedule, right? And it becomes really difficult to reproduce that thread schedule. So this, there are other research groups who have taken forward this idea, this Darwin idea, and tried to use it for multi-threaded applications. Because just like here I am generally using symbolic execution to generate another input, you could use symbolic execution in a similar way to generate another thread schedule, and then compare two thread schedules and find out what is wrong with this. So this issue of reproduction of thread schedules, this has always been there for debugging of multi-threaded applications, and one could solve it this way by capturing the thread schedule constraints as essentially symbolic formula, and then you try to solve this under thread schedules. So there are other research groups. I have given tutorials on this in many international conferences on using symbolic techniques for software debugging. There are other research groups who have come to my tutorials and have subsequently followed this up for multi-threaded. So it's very feasible. But I have myself not done that. In my research group, I have always stayed away from multi-threaded. And part of the reason is that there is already a lot of literature on multi-threaded. So to get into that, yeah.
Thank you, sir. So please remain on stage because we have a small token of appreciation for you, sir. To hand over the token of appreciation, I would like to invite Lieutenant Colonel Dr. Abhik on stage, sir. It was one of the greatest speeches that I ever heard in my life, and I think you also enjoyed it. Now it's time to appoint the new office bearers for the ACM student chapter. For that, I would like to invite Chairperson of ACM student chapter of our university, Himesh Silva. Please welcome to the round of applause.
Good morning, ladies and gentlemen. Professor Abhik Roychaudhury, Vice Dean of Graduate Studies, School of Computing, National University of Singapore. Dr. Abhik, Head of the Computer Science and Engineering Department of University of Moratuwa. Members of the academic staff, members of the Computer Science and Engineering Society, industry personnel, and friends. It is my pleasure to say thank you to the people who have made this event possible after a very interesting and informative lecture by Professor Abhik on a very relevant subject. First of all, I would like to say a big thank you to Professor Abhik for taking time off his very busy schedule to be with us. And also I would like to thank ACM Distinguished Speaker Program which made such a speech possible for us today. I would also like to say a big thank you to Dr. for providing us with the support and guidance needed to organize this event in this manner. Also, I would like to thank staff members and all the industry personnel for being with us and helping us conducting this event, and all of you who are present today. It is my duty as the outgoing chair of the ACM Student Chapter of University of Moratuwa to announce to you the upcoming board for 2014. The chair of the ACM Student Chapter of University of Moratuwa for 2014 will be Ms. Hashmi Senaratna. The vice chair will be Mr. Sumit Vijayadu. The treasurer is Mr. Chamle Vijayratnan, and the membership chair is Mr. Subunathan. I did. And I hope the very best to the upcoming board to continue the activities of Untitled Chapter of University of Moratuwa. Thank you.
Thank you, Rishi. I would like to thank Professor Abhik Roychaudhury again for his precious time, sparing his precious time with us. And now we know our new board of office bearers in the student chapter. Hope everybody will work in hand in hand to make this university, our country, this world a better place. Thank you.